All right, good afternoon. Today we'll be talking a little bit about capacitors. There's a lot of material associated with capacitors on how we arrange the capacitors. We've talked about parallel and series configurations for capacitors. We've talked about energy held in capacitors. We're getting into circuits that are dependent on time, that are containing capacitors. So there's a lot of material, and some of it can be quite challenging. So today we're going to cover a little bit of that material. There'll be probably another video where I'll be more specific about circuits containing capacitors. So one of the main things is to know and to understand how to calculate a capacitance. So there are different ways of calculating capacitance. The first way would be to calculate the electric field inside the capacitor. And then from the electric field, you get back to the change in the potential across the plates of this capacitor. And from the relationship Q is equal to C delta V kappa, out of this, you extract the capacitor from that relationship. Another way to do this, and I'll demonstrate that, another way to do this, and it's a very, very powerful way. We've talked a lot about the power of energy methods. This is starting from energy density, electric energy density. And if you remember, this is little u sub E, and this is equal to 1/2 of epsilon 0 E squared. That's the amount of electric energy held in space per unit of volume due to the presence of an electric field, and space being, of course, free space associated with epsilon 0. That's a term that's, of course, in joule per cubic meters, energy density. From then, you integrate over the whole volume. So you fundamentally do over a certain volume V in which the electric field is located, which will be, of course, the volume in between the plates of the capacitor of UE d tau in elemental volume. That's going to give you the total energy held in space, in the dielectric space, in between the plates of your capacitor. And then you know that this is, you relate that to 1/2 of Q squared over C. And out of this, you'll be able to extract the capacitance of your capacitor. And there's a third method, which is more advanced because it requires a vector calculus, but it's a very important method. And some of you will continue a little bit into this field, will encounter, in fact, most likely in many different fields you will be able to encounter a similar method. It's called the Laplace equation. And it relates a potential function V, and it finally constrains the potential function such that the Laplace of the potential is equal to 0 in free space. So what is this operator? It's a differential operator, the Laplace differential operator. It's fundamentally the divergence of a gradient. So it's a dot product between the divergence, the nabla operator describing divergence, applied to the gradient, to a scalar function, and in this situation of free space, this is equal to 0. So this is a very, very powerful method. It uses the big, heavy tools of calculus to do this. It works in certain situations, especially when the symmetry is reasonably helpful to be able to solve these, because you end up with differential equations. It's not an integral method to start with, it's actually a differential method. But once you get the differential, you're going to have to integrate over this. So again, the integration can be challenging, but in certain situations, it is actually extremely powerful methods. Again, that requires, of course, understanding a little bit of vector calculus. Sometimes this Laplace operator, also called the Laplacian, is also written as nabla squared V is equal to 0. But understanding that this is actually hidden, there is a dot product between nabla and nabla, the divergence and the gradient. So we have seen something somewhat similar in class, because we have seen that the electric field E was the negative gradient of the potential, which we have written in a more formal way as this term. So if I take the divergence on both sides, so I use the Nabla operator applied on the left side, so I have Nabla dot E, that's the divergence of the electric field. This is equal to negative of Nabla dot the Nabla V. So what do I have here? This is equal to rho over epsilon 0. In a sense, this is Gauss's law in the form of a differential equation. We've mentioned that, we've not used it too often, but we've mentioned that. So we have rho, which is the charge density per unit volume, epsilon 0 is equal to negative delta V. I'm going to call this the Laplacian that way. So we see that fundamental relationship that constrains the value of the potential in the presence of charge. In the case of free space, rho is equal to 0, and that gives us this equation. So that's where where this is derived. And in free space, in the space in between the two plates, we would apply this equation. And because this is a second order partial differential, we need to have two conditions, two boundary conditions. And of course, we'll have V at one of the plates they call V sub 0 equals 0, and V at the positive plate will have a certain value of some sort. And this will allow us to solve this differential equation for V in a unique fashion. So the Laplace operator is very powerful. You'll encounter this in fluid mechanics, of course, in electromagnetism, in celestial mechanics, if you look at the motions of objects in space, as well as man-made objects in space. You'll encounter even in image processing. So even if you're a computer science, don't walk away and say, oh, I'm never going to use that. Well, that's a bad attitude to have. You will encounter it. Because this describes the rate at which the average value of V is away from the value of V at that location. So it's, when you think about it, and there's actually an algorithm that uses this, this is exactly the description of trying to figure out where an object ends and another object begins. In other words, this is trying to identify object on an image and be able to detect the boundary between objects and sharpen that boundary. So there's a lot of algorithms based on the use of this type of equations to sharpen. And when you get on your computer and you sharpen an image, there's an algorithm behind that does possibly a calculation based on this operator. So, all right. So we'll see. We'll not do any of these calculations based on Laplace equation. That's why I spent a little more time up front. We'll not look at it anymore. Important method. Instead, we're going to look at applications of the first two methods. But first, before we get there, let's think a little bit about capacitance. What does it mean? And the easiest way to start thinking about capacitance is to consider a sphere of charge, Q. We're going to take a sphere of charge of a certain radius r, holding a charge Q, and as it holds a charge Q, we know that being a conductor in electrostatic equilibrium, it has a given potential, let's call it a certain potential V sub 0. It is an equipotential, the surface as well as the inside of that conductor. And we know there's a relationship between the potential and the charge held by that sphere, and we know this is the same as this is work point charge. We've seen this many times. So the potential V0 is equal to 1 over 4 pi epsilon 0, the charge held by the sphere divided by the radius of the sphere. Classic calculation, we've seen that many times. Now this implies that we have defined a reference potential, and of course we take V equals 0 at a distance r going to infinity. Classic reference value for that situation. So I'm going to extract Q out of this. Q is equal to 4 pi epsilon 0 r times V0. And then I identify it as Q is equal to CV, or C, yes, V0, let's say that. So immediately we see that through basic identification, what is the capacitance of this sphere. That sphere is an amount of capacitance C, which is equal to 4 pi epsilon 0 r. So a couple of observations. First of all, we've discussed in class many times units. This is a capacitance, this is in unit of farad. This is a length, so this is in meters. And a capacitance should always be a product of epsilon 0 times a distance. It scales as a distance, and this is indeed the case, so that indeed represents a capacitance. Notice the 4 pi, because that indicates that we're indeed in spherical symmetry. Now you might say, well, it doesn't look like a capacitor, because in class we always talked about a capacitor as having two metal surfaces influencing each other. That would be a parallel plate capacitor. That could be a spherical capacitor, or that could be a cylindrical capacitor. It could be a conical capacitor. Any two surfaces interacting would be considered to be a capacitor. Well, here this is in a sense an extension of the definition of a capacitance. Capacitance formally relates the amount of charge held by a metal to the voltage that this metal is elevated to. So in a sense, this is a capacitor. But there is something more subtle, because we have this condition right there. So to understand how these two work and to understand that this is indeed a capacitance, we'll get to the next level, which is looking at the capacitance of two spherical shells. So now, instead of just looking at one sphere, we're going to look at two metal spheres, or it doesn't really matter, two metal objects that are influencing each other. And we've talked about capacitors. The easiest form of capacitor are when the two surfaces are totally influencing each other, i.e. one is wrapped around the other. It does not have to be that way. In fact, very often we deal with capacitors that are not designed this way. Here's an example. Here's a wire of an SRP power line. And here's the ground. Well, the ground is not surrounding the wire, but nonetheless, between the wire and the ground, there is a certain amount of capacitance. So, again, capacitance is actually very general. It's it's a lot simpler when we have concentric objects or total influence, but this is in fact more the exception than the reality of everything. So, the first capacitance we've ever encountered was a parallel plate capacitor, and we know that the capacitance for this is equal to epsilon 0, A, the surface area of the plates influencing each other, D, the spacing between the two plates. Again, units, epsilon 0 times a length, that gives the unit of farad. So, now we're going to take two concentric spheres, an inner one, which is going to be a radius r1, and an outer one, radius r2. And we're going to take the inner sphere as holding a positive charge q, and because this is a total influence, the outer sphere will be holding a charge negative q. So here's our parallel plate capacitor, assuming that it is nicely spherical. Yes. And the purpose of this calculation is to determine now what is the capacitance of a spherical capacitor this way. So we'll be using the technique based on the electric field. So we're going to take the first question is, what is the electric field in the space of the dielectric, which is this space here. This is where you have your epsilon 0 material, or any other dielectric, it doesn't really matter. Well, we know that the electric field inside, and I'm going to refer you to what we did based on Gauss's law. We created a Gaussian surface of radius little r, and we calculated the electric field here, which is radial out from the positive, so here's the electric field located right there. And I will refer to what we did in class, which is equal to Q over 4 pi epsilon 0, and R squared. r squared being the radius of my Gaussian surface. And the field is radial and constant on that surface. And then we're going to apply the fundamental relationship between the electric field and the potential, saying that the delta V kappa is going to be equal to the integral, the negative integral of E dot dr, where I am integrating from the inner plate, going from R1 and going all the way to the outer plate, R2. And from this delta V kappa is a change in capacitance going from final plate minus initial plate. Final plate is the outer R2, so this is V minus V plus. So that would be associated with a V minus, and that would be associated with a V plus. And we're saying that this is equal, therefore, to E dot dr. I am moving in this direction, so that will be a small element incremental motion along this direction. Therefore, will be equal to the negative of the integral from R1 to R2, E dot dr, which is simply Q over 4 pi epsilon 0 R squared dr. So that integral is very easy to do. We take the constant terms out. We're left with Q over 4 pi epsilon 0. And then we're integrating that. I'm going to keep the negative sign right here. Dr over R squared taken between R1 and R2. So this is equal to Q over 4 pi epsilon 0. I'm going to take the negative sign associated with the antiderivative R squared, which is negative 1 over R. So I have 1 over R, taking that negative sign right there, and taken between R2 and R1. So that gives us delta V kappa, or V minus minus V plus, is equal to Q over 4 pi epsilon 0, integrating 1 over R1 minus 1 over R2. And we're going to make the assumption that V minus is equal to 0. That will help, or, let's do this. So we take V minus equals 0. That's the inner plate charge at holding negative Q. That's kind of grounding the plate. So we're left with V plus, which will be the potential of my capacitor, equals Q over 4 pi epsilon 0. So now the negative sign is coming in, so I need to flip this. I have 1 over R2 minus 1 over R1. And I hope I didn't make any sign error on the way, which would appear that there is 1 sign error. Where did I get my calculation wrong? So I'm integrating from R1 to R2. Q over 4 pi epsilon 0 1 over R squared. Where is that sign here? E dot dr. E is radial out. Dr is positive. Q over 4 pi epsilon 0 negative. So integrating from R2, which is the V minus minus V plus, negative Q over 4 pi epsilon 0, 1 over R squared, 1 over R, R1 minus R2. It should be the reverse. There's a sign error, I can't see it from where I stand. The formula for the V capacitor should be Q over 4 pi epsilon 0, R2 minus R1 divided by R2 R1. So there appears to be a sign error somewhere, and I don't see it. That happens. And on the board, it's kind of difficult to pick. And I don't see it, I'd like to move on, but I'm sure somewhere there's one of the signs that got flipped somewhere. All right, well, I'll let you check where the sign error is. The purpose of this calculation was to show you how you get to the capacitance, because now you write that Q is equal, extracting Q out of this expression, you get 4 pi epsilon 0, and then you get R1, R2 divided by R2 minus R1, and then times the V kappa. So you get Q is equal to CV, which gives us therefore the capacitor for a spherical capacitor is equal to 4 pi epsilon 0 R1 R2 divided by R2 minus R1. Here it is. Kind of fairly simple expression. Of course, more complicated than a parallel plate capacitor. But now we can analyze it, analyze what happens in certain situations, verify that the units are okay, etc., etc. So let's let's erase this, and I'm going to erase the sign errors that's somewhere buried in here. I apologize for that. And let's look at units. Well, units, we got epsilon 0 times the ratio of distance squared over distance, which gives us a distance, so epsilon 0 times the distance. This indeed gives the correct unit for capacitance. What happens when R2 is much larger than R1? R2 much greater than R1. So that means that for a given inner plate or inner sphere, the outer sphere has a much, much larger radius than the inner sphere. Well, we can check what happens in that formula. And to do that, I'm going to factor out the big elements, big term in the denominator. So kappa for the spherical capacitor is equal to 4 pi epsilon 0. R1, R2 divided by R2, and then I'm left with 1 minus R1 over R2. So no simplification yet, but I'm approaching the simplification because I'm going to do a binomial expansion on this, knowing that R1 over R2 is much less than 1. So now it becomes more or less equal to 4 pi epsilon 0. The R2 cancels out. R1, 1 plus R1 over R2. Here's the kappa in the situation where R2 is much greater than R1. So first approximation, if we neglect this term because it's being so small, what do we find right here? Well, we find the kappa, the capacitance for just a simple sphere that we had earlier. So fundamentally, the capacitance of a sphere is also the capacitance of a capacitor, but the outer shell of this capacitor is sent out to infinity. And that's really what that means when we said that a single sphere had a capacitance of that. That means that the other plate, if you want, of this capacitor was sent to infinity. Another case that of great interest is what happens if I make the spacing between the two plates much less than, say, the radius R1. So I make R2 minus R1, which is the spacing, much less, say, than R1. So in this drawing, that would mean shrinking the outer sphere and make it very, very, very close to the inner sphere. So the inner space, the space that contains the dielectric, should be very, very small. So how does this work? How do we get to this? Well, since the spacing between the two is very small, that means R1 and R2 are going to be about the same. So I'm going to call R1 and call them all equal to each other, and we're going to call it R. And then this distance, R2 minus R1, well, I'm going to call it little d, the spacing now between these two plates. So what does this expression become when I do this? Well, I'm going to have C spherical more or less equal to 4 pi epsilon 0 R1, R2, this is going to be R squared. And then R2 minus R1, this is what I call the spacing V. I rearrange that a little bit. I'm going to write it as epsilon 0, 4 pi R squared divided by D. What is 4 pi R squared? Well, that's the surface area of that inner shell, or that inner sphere, or the surface area of the outer sphere, since they're so close to each other. So this is an area. This is the area of the capacitor. So this is equal to epsilon 0 A divided by D. What do we find? We find that this capacitor behaves as if it were a parallel plate capacitor. So that's what happens when the two plates are very close to each other. Fundamentally, the curvature doesn't look like much. The curvature is very small when you get very close to the inner plate. So it looks like these two surfaces are actually planar and behave as a parallel plate capacitor, which is a very extraordinary conclusion, but born out of the analysis of this calculation for the parallel plate capacitor, for the spherical capacitor. So again, I apologize for the sign error. It's somewhere. I'm sure you'll find it as you look at the calculation. The other thing that I'd like to do about something like that, since we're talking about capacitors, is I mentioned in class that there is another term for capacitor. It's called a condenser. And in other languages also, this is the way capacitors are referred to, as condensers. So where does this term come from? Well, I'm going to try to explain that to you, because that's an interesting aspect of capacitors. So consider again a spherical capacitor. You're going to take a radius R1, and it will have a certain capacitor C1 like we saw earlier on, 4 pi epsilon 0 R1. And this capacitor is being charged. It's holding a certain charge Q1, and of course at a certain voltage V1. So I would have Q1 equals C1 V1. Nothing new about that. And I'm holding this voltage V constant. V1 is held constant. It might be connected to a battery, for example. That's what I want to do. And then I'm adding around this shell, this sphere, I'm adding another one. So now I'm forming the spherical capacitor that we had earlier. And I'm holding this shell at a certain potential V equals 0. So I'm putting myself back in the same conditions that I had earlier. And this is a radius R1, this is a radius R2. So what happens? Well, as I introduce this new conductor surrounding the inner shell, inner sphere, then I'm creating a new capacitance. I'm going to call it C12, corresponding to the capacitance of this sphere 1 and 2 together. So we know this is equal to 4 pi epsilon 0 R1 R2 divided by R2 minus R1. Right? So then I'm going to manipulate this business. I'm going to call this little distance little e. So I'm calling R2 minus R1 equals E. That's the spacing of your insulator, the dielectric material. So then I'm also looking at this term, 4 pi epsilon 0 R1. That's C1. So this is going to be C1 R2 over E. R2 minus R1 is E. But I'm going to modify it still slightly. I'm going to call it C1. R2 is R1 plus E divided by E. And just basic manipulation. So I end up having something that looks like C1 1 plus R1 over E. This is the new capacitance C12 created by bringing this outer shell around the inner shell. So what is the new charge Q prime held by the inner shell? Obviously, as I create a capacitor, there'll be charge motion. The batteries are responsible for feeding charges or taking charges away in order for these voltages to remain constant. So there will be a new charge held by the inner shell, and that new charge will be equal to, well, it's going to be equal to the capacitance of this new capacitor, C12, times what? Well, it's going to be times the voltage, and since the voltage is constant, it's going to be times V1. So what is C12? Well, it's C1, so I'm going to have C1 V1, and then 1 plus R1 over E. But what is C1 V1? Well, that was my original charge. So I'm showing that the new charge is going to be the original charge Q1, 1 plus R1 over E. What is that telling us? Well, this is telling us that I can make Q prime 1, the new charge held by now the true capacitor, vastly larger than Q1, because I can make R1 over E much, much greater than 1. By making, for example, this spacing very, very small. That's going to make this number very large, therefore Q prime 1 would be much larger than Q1. So just by bringing another sphere surrounding the inner sphere, I am capable of increasing the amount of charge held by this. In other words, it's as if I was condensing charges, just like water vapor condenses on the surface that's cold. Here, the same analogy, I am condensing charges as I influence the outer environment of my inner shell. So that shows that to get a lot of charge, you want to create a capacitor. Just a sphere by itself is not sufficient. You're not using the full capacity, which is the appropriate word, of what you can do. So this is the purpose, this is why it's called a condenser, which is another word for capacitor. Capacitor sounds like it has a capacity to hold charge. Condenser, it condenses the charge. It's a beautiful expression, I believe. All right, so let's do another calculation of capacitance. This time we're going to use the energy method. And we're going to apply that to the cylindrical capacitor. Another classic structure for capacitor, in fact, much more common than a spherical capacitor. An application, well, let's do a drawing first here. Here's an inner cylinder, which has a radius of R1, and I'm surrounding it by an outer metal cylinder, concentric with the inner cylinder, and it would have a radius of R2. And the purpose of this calculation is to determine the capacitance of this structure. So I am holding the inner at V plus and the outer at V minus, which I can also call V0. It doesn't really matter what it is. So I have a certain height h, and I want to use the idea of the energy density, 1/2 of epsilon 0 E squared. E being the electric field held within the dielectric in between the two plates. Once again, I'm going to refer you to the calculations we did way back then for the electric field in the inner space. Q over 4 pi epsilon 0, the value at a given radius little r from the center of that structure, and then times h being the height of that cylinder. So we have seen it in a slightly different form because we were using sigma as opposed to Q. But because I'm interested in figuring the capacitance and Q is equal to CV, I am holding that variable Q in the value of the electric field. I am not transforming it in the form of sigma. Therefore, now I want to calculate what is the U electric held well, in fact, I didn't want Q equals CV, but 1/2 of CV squared. Or 1/2 of Q squared over C. So, U electric, this is going to be the integral of UE, so 1/2 of epsilon 0, E squared. I'm going to have so Q squared over 4 squared pi squared epsilon 0 squared H squared. I have an R squared that comes up. And then I have the d tau. D tau is going to be this elemental volume, and I'm integrating over a cylindrical volume. So I'm going to take a small cylinder of thickness dr of height h and calculating its elemental volume. So what is the elemental volume d tau of such an elemental cylinder? Well, it's going to be 2 pi r is going to give me the circumference of the circle, times dr is going to give me the volume held on that little cylindrical shell that I need to multiply by h to get the full volume. So it's going to be 2 pi r dr times h. So unit-wise that works. I got 3 lengths corresponding to a volume. That works. Now we're ready to integrate and do a little bit of simplification on the way. U electric. Of course, I'm integrating over the volume, but this volume integral is finally a single integral, a line integral along the distance r. So I'm going from the inner r1 to the outer r2. So what do we have? We have 1 epsilon 0 that cancels out. We're going to have a pi that will cancel out. So I have to be careful. Let's do Q squared over let me do this. U electric. The integral of r between r1 and r2 of Q squared 2 pi h r dr divided by 4 pi squared epsilon 0, one of them is gone, h squared r squared. Alright. And there might be a factor of 2 that should still be down here. So let's take everything that's constant out. Q squared. I have a 2 pi and a 4 pi squared. So the 2 and 2 cancel out. One of the pi's cancels out. So down here we get 4 pi epsilon 0. H term, I have an h and x squared, so I have an h down in the denominator. And r terms, r over r squared, that gives me just one of them, and that stays in the integral dr over r between r1 and r2. Here's the amount of U electric held inside this capacitor. I think this one, I didn't make any errors. Okay, we continue on. The integral is fairly straightforward. This is an ln taken between R2 and R1. That gives us a U electric equals Q squared divided by 4 pi epsilon 0 H ln of the ratio R2 over R1. And then we do an identification because we know that the U electric is equal to the expression as a function of Q, which is 1/2 of Q squared over C. And we identify term by term. So the Q squared is there. The C is going to be extracted out, and we get to take care of the 2. So the capacitance is equal to, I'm going to have to flip this, divided by 2, so I'm going to left with 2 pi epsilon 0 h and then divided by ln of R2 over R1. Here is the capacitance of a cylindrical capacitor of inner radius R1, outer radius R2, height h, with the dielectric as free space. Again, unit-wise, you see that it works because an ln, in physics, ln is always unitless, so it's always ln of a ratio of two things that have the same unit. No units here, epsilon 0 times the length. This is indeed the unit for a capacitance. Notice that very often, from a practical perspective, we're interested in the capacitance per unit of length. So C per unit of length, CL. So that means per unit of length of this cylinder. So we divide by H, and that becomes 2 pi epsilon 0 divided by ln of R2 over R1. And this is in farad per meters. That's an important calculation because fundamentally that structure is your coax cable. You have an inner conductor and an outer conductor. Very often the outer conductor is grounded. This is that mesh that surrounds the inner conductor that carries the signal. So it would have a capacitance per unit of length of that amount. All right, let's shift gears a little bit, switch gears a little bit, and do another type of calculations on capacitors. So now we've seen how to calculate the capacitors using an energy method, which is very powerful, as well as using the basic relationship between the electric field and the capacitance, and the electric potential. So let's do maybe a calculation of energy transfer. So let's consider a very basic circuit where we have two capacitors that are also connected in between with a resistor R. And we assume that the capacitors are or capacitor 1 holds a charge Q1 and was initially charged at voltage V1, and it has a capacitance C1, and this one is a capacitance C2. So that's the initial situation, if you want, before the switch is closed. So this is that situation where we have a Q2 initial equals 0, there's no charge on this capacitor, and that will be the Q1 initial. And at a certain time, we close the switch, and the question is, determine the energy held by these two capacitors and compare to the initial energy that we had initially. So it's a conservation of energy type of calculation. So what do we have in terms of initial, let's talk about what is my U electric initial. Well, this is going to be the electric energy held by this capacitor. It's equal to 1/2 of C1 CV squared. Or because I'm going to probably also calculate that, it's going to be the same thing as Q1 squared over 2C1. That's going to be the initial, Q1 initial, held by the system. I close the switch. So now the switch is closed. The circuit is a closed circuit, which allows the charge initially held by this capacitor to get redistributed between the two capacitors. So we have, of course, a condition, the conservation of charge, which states that what we had initially, which was Q1 initial, will be equal to what I have at the final situation, which is Q1 final plus Q2 final. So as I close the switch, I have a transient phenomenon. I have current flowing, charge being exchanged, and at the end of that transient phenomena, I will have regained electrostatic equilibrium. There will be no current. If I have no current, so after Q1 discharges, you get another electrostatic equilibrium. And once you have the electrostatic equilibrium, that means the current flowing has become zero again. If I have this no current flowing, that means I have no voltage drop across the resistor. That means that the potential across this capacitor is equal to the potential across this capacitor. They hold the same amount of potential. They hold different charges because they have different capacitance, but they must have the same potential. So that's a very important condition. That means the delta V kappa for capacitor 1 is equal to the delta V kappa for capacitor 2 in the final situation. What does it mean? In the final situation, I have, so Q is equal to CV. That means that delta V is equal to Q over C. So I have Q1 final over C1 equals Q2 final over C2. Here they are. That gives me a second equation, linear equation, connecting the charges, which is really what I need. So now it's a matter of elimination. We're done with the physics, and we extract, for example, out of this one, Q2 final, writing it as C2 over C1, Q1 final. Substituting into the conservation of charge, we got Q1 initial equals Q1 final plus Q2 final, so therefore plus this one, 1 plus C2 over C1. Oops, I already took the Q1 final. Therefore, I extract Q1 final equals, reducing this to same denominator, I'm going to have C1 divided by C1 plus C2, Q1 initial. Here's the first one. As far as Q2 final, well, that's pretty easy because Q2 final is C2 over C1 times Q1 final. So C2 over C1, the C1 cancels out. That means I am left with C2 divided by C1 plus C2, Q1 initial. Here is the second value of the charge I was looking for. So what is the U electric final? Well, it's going to be made of the electric energy held in capacitor 1 plus the electric energy held in capacitor 2. So this is going to be 1/2 of using the Q squared formula. So Q1 final squared divided by C1 plus 1/2 of Q2 final squared divided by C2. So what do we get? Well, Q1/2 is going to be present in both of them. Q1 final squared over C1. So I'm going to have C1 squared over C1. I'm left with a C1 in the denominator, numerator, divided by C1 plus C2 brought to a square, times Q1 initial, plus Q2 final. It's going to be the same gymnastics. C2 divided by C1 plus C2 brought to a square, and then the whole thing is a factor of Q1 initial squared. Here's the U electric final for that situation. So, of course, that simplifies quite a bit. I can now get rid of all this. So same denominator, so you let numerator you get C1 plus C2 divided by C1 plus C2 to a square, one of them cancels out. You get U electric final equals 1/2 of Q1 initial squared divided by C1 plus C2. Voilà. So, we have our initial and we have our final. They should be equal to each other. We should have, you think we have conservation of charge. We have conservation of energy. Why are they different? Well, then we need to think about what happens during that discharge. During that discharge, we mentioned we have a transient phenomena where we have a current that will be circulating through the circuit. And the current carries a charge from capacitor 1 to capacitor 2. That current passes through the resistor. The resistor, one of its role is to dissipate some of the electric energy and transform it into thermal energy. So here goes where the energy that we're missing. Because of course, we have U electric final less than U electric initial. We have lost some electric potential energy. And that loss is to be found in the thermal energy that was released by the resistor during that transformation. So by how much? What will be the U thermal, the U joule, the joule energy released by that? Well, it's going to be the difference between the two. So this is going to be 1/2 of the difference between the two, 1 over C1 plus C2 minus 1 over C1 times Q1 initial squared. So this is equal to, reducing same denominator, the numerator will have C1, C2, squared, yes. That would be 1/2 of C2 divided by C1 plus C2, Q1 squared, with a negative sign because this is energy that's been released. We have less energy that we had. So if you wanted just to calculate the amount of electric potential energy that's released from a thermal perspective, you'd have a U joule as just 1/2 of that value. So then you can look at really what happens. What would be the most efficient way of transferring energy? That is, how would you minimize U joule? Well, you would look at it as a function of, say, for example, capacitor 1. And you would plot this function as a function of the value of capacitor 1. And you would look at in which situation would you have the most optimum transfer. Or you can think also in terms of C2, do the same thing, consider it as a function of C2 for a given C1. And what would be the optimum transfer to minimize the amount of energy released through Joule effect. It's a very interesting little problem, an interesting application to this, an extension. I'll let you do that. There's another interesting aspect to this. You might say, okay, first of all, it's interesting because nowhere does the resistance show up in these calculations. Correct. The resistance is there as a current limiting element. What if there was no resistance? What if I was getting rid of that resistance and just allowing the conductors to be connected, the capacitors to be connected, and allowing the discharge of one to the other? Well, then you would have an extremely large current, a very large spike of current. And you guys say, well, then there's no loss anymore of energy through a resistor. So you should have the same amount of energy at the beginning that you have at the end. But finally, the calculation is not going to change for us because the resistor was not even showing up in any other calculation. So why at the end are we going to have this difference in energy? Where is this energy going to get lost? Okay, then you're going to argue, okay, well, maybe some of it gets lost through these quote-unquote ideal wires that still have a little bit of resistance. And if it's the only resistance, they're also going to be producing a little bit of thermal energy. Okay, But what if you take this to helium temperature and you have now superconductors? You have zero resistance. Well, the calculation will remain the same, of course, assuming capacitors can do their job at such a low temperature. But what happens is, and we'll see later on through this semester, is when you have a very sharp increase in current like that, a burst of current, you have actually radiation that's emitted. You have electromagnetic energy that's being radiated out. And electromagnetic energy depends on the change of the current, the rate at which the current changes. So when you have no obstacle to the path of the current, that rise in current is going to be extremely fast, and you have a lot of energy that's going to get dissipated out, not in the form of thermal energy anymore, but in the form of electromagnetic radiation. Interesting little aspect to this problem. All right, what I'd like to do now is to do a little bit of a very basic calculation on charge held by capacitors and how they get distributed between capacitors. An extension a little bit of this, but now looking just in terms of charge, no energy. And these are classic examples, and you'll see them in the homework. You'll see them most likely in the test, one way or another. So let's take a simple calculation of a battery of EMF E, call it 9 volts, connected to a set of capacitors, such that we have capacitor C1 in parallel with capacitor C2, and connected then this whole arrangement connected in series with capacitor C3. And we given the values for C1, which is 4 microfarad, C2 equals 12 microfarad, and C3 equals 2 microfarad. The question is, calculate the Q's and calculate the delta V's on each of these capacitors. So this is a classic example, and you'll see that structure repeated over and over again in these type of exercises. You always follow that same pattern, that same structure. So first thing you need to do is combine all these capacitors into one single equivalent capacitor. First step. So the first step is calculate capacitor equivalent, C equivalent. So first thing, we have C1 and C2, which are in parallel with each other. Two capacitors in parallel add up to each other. So I would have C1, 2, which would be the equivalent capacitor of C1 and then 2, would be C1 plus C2. C1 plus C2 would be, therefore, 16 microfarad. And then we need to calculate the C equivalent. For now, I have transformed my circuit now into a C12 followed by C3. And this is still connected to the battery. So now I have two capacitors. They're in series. So the equivalent capacitance is 1 over the sum of the two capacitors. And then I never forget to take the inverse of that. So what do I have? I have 1 over 16 plus 1 over 2. And I will take the inverse of that. So when you do the calculation, you get your C equivalent as 32 over 18 microfarad. Here's step number 1, which was to calculate the total equivalent capacitance of that circuit. So now I am down to a circuit that is simply one C equivalent connected to the battery. So we've reached the bottom part of the calculation. Now we're going to be climbing back up, because out of this, we're at the bottom. Out of this, I can calculate what is now the voltage held by this, the charge held by the capacitor, because I have one single capacitor connected to the EMF E. So what is the Q equivalent? Well, we know that Q is equal to CV, V being the potential across the capacitor, which is equal to E. So the Q equivalent, the charge held by the equivalent capacitance is equal to C times E. And if you multiply, therefore, 3218 times 9, you get 32 divided by 2, which is 16. So you get Q equivalent equals 16 in terms of microcoulombs. All right, now we backtrack. So we've gone through this route all the way down. We've calculated now how much charge is held by this. We know the potential across this, and then we backtrack. We get back up to this level of the calculation. So we have here now two capacitors that are in series connected to a battery. These two capacitors, there's one thing that they must have. They must hold the same charge, necessarily. So I must necessarily have Q3 equals Q12. The charge held by 3 is equal to the charge held by 1,3. The reason is because the inner part of the capacitors, the inner plates, are initially neutral. So if they're initially neutral, the only possibility for them is to hold the same amount of charge. So if these hold the same amount of charge, one will be a positive Q, and the other one will be a negative Q. That would correspond to, therefore, a positive Q acquired by this upper plate and a negative Q acquired by that upper plate. These charges, every time you have capacitors in series, initially uncharged, then they will hold the same charge. In fact, even if they were initially charged, when you connect them in series, they will share that charge. So this is that situation, Q3 equals Q12. So, and what is going to be this charge? Well, this charge is the same as what we had originally down here. You cannot create more charges, so this is necessarily equal to 16 microcoulomb. That allows us to calculate the delta V3. Why? Because from the delta V3, we get Q equals CV. So this is going to be equal to Q3 divided by C3. C3 is 2 divided by 16 equals 8 volts. Delta V12 is the same thing. This is going to be Q held by 12 divided by C12. We've calculated C12 out here, which is our 16 microfarad, and Q12 is 16 microcoulomb. This is going to give me 1 volt. Voila. So we have now solved this circuit. We still have one step, which is to go from this to that circuit. And that circuit now, the only thing we have to worry about is this element going from a 1 equivalent capacitor C12 to coming back to that situation where I have 2 capacitors in parallel. Well, that's also fairly straightforward, because if I have 2 capacitors in parallel, I know that I have necessarily delta V1 equals delta V2. And that's such that it's equal to the delta V across the original 1,2 equivalent capacitors. So what is the charge held by Q1? Well, it's going to be C1 times delta V1. delta V1, delta V12, which is 1 volt, times C1, which is 4 microfarad, we get Q1 equals 4 microcoulomb. And what is Q2? On the same principle, Q2 is going to be C2 delta V2. Q2 is going to be equal to C2, 12 times 1, 12 microcoulombs. We have now all the information corresponding to these capacitors. We have the voltage across them, we have the charge held by them, we've solved our problem. So classic problem. We start from the beginning, from what is given to us, the circuit. If we have any capacitors that can be rearranged into equivalent capacitors, we do so. And we proceed step by step. We redraw the circuit as we move along until we reach just one single capacitor connected to the battery. Then we manipulate this capacitor to extract what is the information that we can, which is going to be, of course, the charge held by this capacitor. The voltage is known. And then we backtrack. We go up one level and up one level until we reach the very beginning, and we have then all our unknowns solved. All right? So I'd like to do maybe another little exercise. I have a couple others, but maybe we can do one that's a little more advanced. A little more advanced capacitor and trying to reorganize capacitors in a simple fashion. So you're given a circuit that contains capacitor, and the idea is to find what is the equivalent capacitance of that circuit. Again, classic calculation, but sometimes it can get pretty complicated in certain situations. So here's the situation here. You're given a capacitor that we're going to call capacitor 1, connected through this capacitor here's A and here's B. All the capacitors have the same capacitance, C, and this is going to be capacitor 1, capacitor 2, 3, 4, 5, and 6. And I'd like to be able to calculate what would be the equivalent capacitance, i.e. the capacitance that would be just that one capacitance between A and B. What would be this C equivalent? So some of these problems can be a little challenging, and this one is a little bit challenging, and it took me some time to figure out what it is, but I found it. So I thought that was an interesting one. So it's just now it's a matter of redrawing this circuit in a different way, looking at things from a different perspective. So maybe the easiest perspective to start with is to look at what happens starting at point A. Now I'm looking at, as I move across the circuit, what am I encountering? Well, point A here is the same, by the way, as point A here, because these are all ideal wire. So first thing, I encounter 1, and I encounter 4. That brings me back to B, the end point. So maybe what I can do, starting at A, going all the way through capacitor 4, which is going to be above all this business, and ending back at position B. So I have now traced this part of the circuit. Right? Then what do I have? From A, I first encounter capacitor 1. Then capacitor 1 is also in parallel with 2. Capacitor 2. And then what happens? As I continue to 1, I encounter 6. And capacitor 6 then is reconnected to B, so it goes back to here. Out of 2, I'm here now. I have a continuation to 3, capacitor 3, that takes me to between 1 and 6. Here it is. And then what am I missing? I have 4, I have about 5. 5 connects between 2 and 3 and connects back to B. So 5 looks like that. Here it is. Here's that modified circuit where we start to rearrange the capacitors in order for us to be able to understand a little bit how that works. All right, it's still not clear, so we want to reorganize things a little better. So what can we do? Well, we redraw A. You're going to have 4 going on the top. That one is isolated and stays there. Then, well, look what happens here. I have 1 to 6 to B. So I'm going to draw it this way. 1 to 6 to B. Now from 1, I go to 2. From 2, I go to 5, back to B. So I go to 5 here, back to B, which is all this line, so I go back here. And the last one that I'm missing is 3. 3 connects between 2 and 5, 2 between 1 and 6. Here's 3. So that looks already a lot better than this mess. We start to see some symmetry and some reorganization. So, there's an interesting observation. That's really the difficult part of this problem, is to realize that these 2 points are really equivalent to each other from a voltage perspective. You have full symmetry in your structure. 1, 6, 2, 5, and then the 3 connecting these 2 positions in between these 2 capacitors. So you have symmetry. And what that means is that the potential between these 2 points are equal to each other. So I can think of it as if I had a wire that was connecting parallel to this capacitor and doing this business. That was the challenging element. To realize that this capacitor, these two leads are fundamentally the same due to symmetry. So I can rearrange this organization of capacitors into something that's even going to be simpler. I'm going to say I have 1. From 1 is in parallel with 2. Then because this lead here and this node here and this node here are equivalent, I can regroup them as 1. And then what do I have? Well, in continuation to 1, I have capacitor 6. And in continuation to this lead, I have 3 and 5 that come together. And at the end of this, I go back to B. Voilà. So now we have a set of 2 capacitors in series, in parallel with capacitor 6, and then we have another set in parallel. The whole thing is in series, and then another set in parallel. So now this is totally manageable. Another way to draw it would be to say that I could draw the lead to do this business. So in other words, now this will be equivalent to having capacitor 4 here connected to 1 in parallel with 2 and 3. then reconnect it to 6. And the last one that's sitting by itself, 5, and up to B. Wow. These two configurations are exactly the same, we just, depending on where you put capacitor 3, because again, these two nodes are equivalent to each other. So I can combine 3 with 2 or 3 with 5 in the lower portion of that circuit. And this is of course because the capacitors are equal to each other. So now it's just a matter of regrouping everything. Say I work on this one. This one I have, each capacitor has a capacitance of C, they're in parallel, so they double up. I have 2C right there. Here I have capacitors in series, so I'm going to have out of this just 1/2 of C. And 1/2 of C, the whole thing right there is going to be 1/2 of C in parallel with C, so plus C. This is going to be equal to 3/2 of C. So the lower branch, I'm going to write it here, I have 2C in series with 3/2 of C. So I'm going to have a total capacitance of 1 over 2C plus 1 over 3C over 2, inverse of that. And in fact, I didn't calculate it. So this is the same thing as 1/2 plus 2/3, inverse of that, and then 1 over C in front of it. So this is 6, 3 plus 4, 7, 7, 6, 6 over 7. So the C equivalent is going to be 6 over 7 of C. 6, 3, 4, 7. Here we go. So now I have this whole part here is equal to 6C over 7, which I have in parallel with 4. So the net capacitance for this is going to be 6C over 7 plus 4C. Assuming no errors were made, this would be the total equivalent capacitance, the big C equivalent for this whole circuit. That would be equal to 28 and 6, 34 over 7 C's. So this was a little bit challenging because of the 3 capacitor right there, that capacitor number 3 connecting these two terminals, these two nodes of my circuit. But the principle is the same for any other type of arrangements of capacitors. You have to do multiple drawings to start to reorganize them in a way that's a little more amenable to basic calculations, i.e. bring them back down to something that we know how to deal, which is basic parallel configurations as well as series configurations. Something like that was kind of intractable to solve until you could resolve it in these very basic configurations. Okay, I have one more little exercise that will take us about 10 to 15 minutes. I'm going to try to go fairly fast, but it's an important one for the methods also associated with solving some of the capacitor problems. And this time we're going to look at the force acting between parallel plates of a parallel plate capacitor. That method, in fact, is applicable to any form of capacitors, any geometry of capacitors. So we're looking at the situation where we have a parallel plate capacitor, negative Q, positive Q, or negative sigma, positive sigma. And looking at what is the force necessary to to hold the plates apart. What is the force F required, necessary to hold the plates apart? So we know there must be a force F that's designed, that is there to hold the plates apart, because the plates being oppositely charged, they want to come together. So something must be holding it. In practical perspective, what holds it in a capacitor is really the dielectric. The dielectric has a responsibility, has a mechanical responsibility of keeping the plates separate and holding them apart. So to do this, there are different methods to do that, but I want to do a method based on energy. It's an extremely powerful method. Again, so we're going to assume that this capacitor has been charged, plus Q minus Q, and we're going to assume that the capacitor is isolated. Isolated means that the Q is equal to a constant. The Q does not change anymore, it is held constant. So we know what the energy of the capacitor, the U electric, or the U kappa, well, think in terms of the capacitor. So this is a capacitor that has a capacitance of C and held at held a certain potential, but we don't care about the potential, we care about Q because this is what is constant. So we have to use the Q squared over C expression because of Q being constant. And then I'm going to say, what if I were to move this plate by a small amount dx? And that's a classic method to solve these problems. I'm going to calculate what is the elemental work dW that the operator does. So I'm going to say dW of the operator. To remind you that this is the external force acting on the capacitor. It's the work that it performs that we're calculating. Well, it's going to be equal to F dx, the product of the force times the displacement. So I can do a nice little axis, we'll call it the Z axis if you want, going vertical, with a small displacement, well, we have to call the X axis if I do a displacement X, with a spacing of X between the two plates. So I'm doing an infinitesimal displacement of the plate, and I'm calculating the work that the force needs to perform to produce that. So as I do this, what am I doing to the capacitor? Well, I'm increasing the spacing of the capacitor. If I increase the spacing of the capacitor, that means I decrease the capacitance. If you remember, for a C for a parallel plate capacitor, this is equal to epsilon 0 S over the spacing D, or call it X. So as X increases, capacitance goes down. Capacitance goes down, the electric potential energy held by the capacitor goes up. So by doing work on the capacitor, I increase its energy. And by how much? Well, I create a certain amount of du capacitor. The gain in the electrical energy held by the capacitor is going to be equal to 1/2. The Q is constant. That's why we chose it, because it makes it easy. And then the only thing that varies is C, so this is D. The small variation of the capacitance, which is in the form of 1/C inside that function energy. And all I need to do now is the amount of work that I do on the capacitor, being quasi-static, so I'm not producing any kinetic energy, is exactly equal to the change in energy held by the capacitor. So I write that F dot dx is equal to 1/2 of Q squared D over D. D over D. I'm sorry. Oops, I'm going slightly ahead. D over 1/C. Divides both sides by dx. I have the force F equals 1/2 of Q squared D over dx of 1/C. Here's the value of the force when we are at Q equals constant expression. That is not dependent on the shape of the plates. It could be spherical, it could be cylindrical, it could be parallel plate capacitor, it does not matter. All we would have to know is how the capacitance changes with the spacing between the plates. So we would now have that actual formula for the capacitance. In the case, of course, of a parallel plate capacitor where we have this, what is 1 over C? 1 over C now for the parallel plate capacitor. Well, it's X divided by epsilon 0 S. So what is d over dx of 1 over the capacitance for a parallel plate capacitor? Well, it's a derivative of that with respect to x. Well, it doesn't take a lot of calculus to realize that this is equal to 1 over epsilon 0 s. So if I inject all this into the value of the force, F becomes 1/2 of q squared and then divided by epsilon 0 s. Here is the amount of force. Actually, I should have probably called A to be consistent with what we did in class. Here we go. Here is the amount of force that is required to hold the two plates apart when the capacitor is holding a charge Q. So this was calculated based on this condition. But this formula should not be dependent on the condition. Whether the plates are moved, the force is what it is. It's not dependent on really how you've calculated it. So we expect that if we were to do the same calculation based not on Q constant but V constant, we should have the same formulation. Well, we'll see if that's the case, and that's going to be a little more difficult. Couple things to observe. Notice that X doesn't show up in there. I say, wow, this is crazy because force is therefore independent. Well, independent on the position. Well, you got to be careful with these formulas. Now, we were doing this calculation based on the small displacement, assuming constant Q. But Q is still equal to CV via the capacitor. And the capacitance is still equal to epsilon 0 A over X V. So I can still replace my Q by this relationship. That's still valid. So what does the force become? 1/2 Q squared becomes epsilon 0 squared A squared divided by X squared. Then I have an epsilon 0 A that comes from here. And then I multiply this by now V squared. So the force is therefore dependent on epsilon 0 A divided by 2x squared V squared. There is an alternate way of writing that expression which now shows that indeed it's dependent on the spacing which it should be. You expect it to be. This is interesting because we've used that condition Q equals constant, and then we end up with a formula that re-brings the voltage. That's perfectly acceptable. There's absolutely no problem with that. That method of assuming a small displacement is called the virtual work method. A very powerful method that you will encounter it when you start doing various forms of mechanics. This is a classic example, very powerful method. So we're going to keep this in the back of our mind, and we're going to look now at a different way of calculating this in terms of constant potential. Instead of constant charge, we're going to be assuming that the capacitor is attached to a battery that maintains its charge. Alright, so now the capacitor is at constant voltage. So the U kappa that I'm going to be probably using will be the one that contains the capacitance, 1/2 of CV squared, the potential. I'm going to do the same business. I'm going to say I have a capacitor that is holding a certain amount of potential because it's connected now to the battery, or held a certain potential because it's connected to the battery. I'm going to slowly change the spacing between the plates. What do I get? Well, I'm going to calculate what is the dW of the operator that is doing the motion. It's the same thing. It's still going to be equal to F dx. No change on that. What is the change in the value of the capacitance? The capacitor energy? held by the energy held by the capacitor. Well, V is constant, so this is going to be equal to 1/2 of dc V squared, the infinitesimal change of the capacitors. And now what I'm going to do is I'm going to equate those two things. What's going to happen? Well, I'm going to say that F dot dx, the amount of work that the operator does on the capacitor, results in a change in the energy held by the capacitor of that amount, dCV squared. Divide both sides by dx, which is going to be 1/2 of dc over dx, V squared. Here's that formula for the case where V is held constant. Now if I apply this to the parallel capacitor, again the capacitance is epsilon 0 A over X. What do I get? I get the force is equal to 1/2 dc over dx epsilon 0 A over x squared, but there's a negative sign that shows up because of the derivative of s times V squared. Well, that's almost that one, except for the negative sign. And then we start to reflect that what is going on. We have calculated the force acting on the plates through methods where the plates were moving while the charge was held constant. And then we do the same calculation while the capacitor is held at a constant potential. And we get kind of the same magnitude, but there's a change in sign. This would indicate that actually the force for me to move this would be pointing down. It makes absolutely no sense. What's going on? And that's an interesting problem. That's why I like it, because we need to really reflect on what that means. So I'm going to keep this as, so this was F based on Q equals constant. And I'm going to write F that is based on V equals constant. And we know this is incorrect, but I'm going to keep it this way, negative 1/2, or I'm going to write exactly the same, it's just a negative, epsilon 0 A over 2x squared, V squared. I'm going to keep that, knowing that this is actually most likely incorrect. What is the issue? Well, we have to reflect on what goes on. When we have this capacitor connected to the battery, what goes on? As I move the plates, the battery is going to start to feed charges onto the plates. And the reason it does so is because it wants to maintain the same potential. Think about what happens. I have Q is equal to CV. Right? By changing the spacing, I am changing C. If I change C, then necessarily these things have to get readjusted with each other. V is held constant. So necessarily the battery has to change that. So my Q is changing. How is it changing? That means the battery delivers charge. Or it takes charge away. Depending on what happens, whether bringing it up and down. But the idea is the battery is forcing some circulation of charge into the capacitor. If it does so, the battery does work as well. It transfers charges onto the potential of the capacitor. So we have to take this into consideration when we calculate the energy terms. And that's where it's going to be changing totally the way we do things. So let's get rid of that here. And we're going to redo this calculation now by thinking in terms of the amount of work that the energy is, that the battery is doing. So the battery will be transferring some dQ onto the plates. So a positive dq going here and a negative dq coming there. Or in a sense, it's taking away some dqs, some negative dq from the plate. So what is the amount of energy associated with that motion? Well, the amount of energy that the battery developed is going to be the dq times the potential at which the capacitor is held. So the V kappa. That's the amount of work that the battery has to do to push this charge up to the potential held by the capacitor at that moment. And we know that this voltage of the capacitor is constant anyway because it is controlled by the EMF of the battery. But what is that amount of dq? That dq. Well, that dq is going to correspond to a change in the capacitance times the voltage V of the capacitor. Right? This dq equals CV. So the dq is V being constant corresponds to a change in the capacitance. So a change in the capacitance, in a sense, held at a given voltage requires this amount of dq to be injected in a capacitor for this relation to be correct. So what is the amount of dW, the work that the battery does? dW of the battery. Well, the dW of the battery is dq times V of the capacitor. But the dq of V of the capacitor is finally dC times V kappa squared. Here's the dW of the battery. So now we have the amount of work that the battery does, and we need to add it to the amount of work that the operator does to know by how much the energy of the capacitor changes. So we write again the same equation in the sense that dW of the operator plus now the work additionally that the battery does should be equal to du kappa, the change in the capacitance, the energy held in the capacitor. The capacitor's energy changes due to the operator doing work, as well as the battery doing work by feeding charges as the spacing changes. So now we're back to on our track, and we can then do this calculation. What is the D of the operator? Well, it's still F dx. What is the dW of the battery? Well, we said that was plus dC V kappa squared. That should be equal to the change in the electric potential energy of the capacitor at constant voltage, which is that term, 1/2 of dC V, I'm going to use kappa again since I've used it here, V kappa squared. Here's that new equation, which is now the equation of conservation of energy, looking at the new term corresponding to the energy that the battery develops and feeds into the capacitor. All right, so now we have it. What do we notice that you have 1/2 of dCV squared minus dCV squared. So F dx becomes negative 1/2 of dC V kappa squared. Now, what do we have? dC is equal to what? Well, it's, if you remember, it's d of epsilon 0 a over x, which is now negative epsilon 0 a over x squared times dx. Or in fact, what I should have done, it works that way, but just to make it simple, gives you f is equal to divide both sides by x, negative 1/2 of dc over dx v kappa squared. So dc over dx, we've seen that, is equal to negative epsilon 0 a over x squared. Reinjecting this in there, I get now the force required to hold the capacitor. Notice negative negative cancels out. 1/2 of epsilon 0 a over x squared v kappa squared, which is now held at v constant. And guess what? Now we land on exactly that same formula. So the ticket was to realize really that there's another form of energy coming in, which is the energy associated with a battery. And the last little element to show you on this problem, and we'll close it on this, is to show you that these two expressions are really equal to each other. Let's start with what we had earlier for Q constant. And if you remember, we had Q squared over 2 d over dx of 1 over c. That was the force that we had found earlier when the Q was constant. General, it doesn't even now relate to parabolic capacitors, it's a general form. So I'm going to modify this a little bit. Q squared over 2. D capacitance is a function of x. So d over dx of 1 over the capacitance, I can also transform it as 1 over c squared dc over dx, and then with a negative sign because that's a fraction. So this is the same thing as negative q squared over 2c squared dc over dx. Now, what is q squared over 2? Q squared over c squared? That's v squared. It's negative 1/2 of v squared dc over dx. So where was I going with this? Suddenly I lost my train of thought. Oh yes, because this is the expression we found for the force when V was constant. Which shows that these two value the force from the most algebraic perspective, irrelevant whether it's a parabolic capacitor or a different form of parabolic capacitor, it doesn't matter. The force, whether you calculate in terms of constant Q and constant voltage, is the same, which makes sense. The force is what it is. The two plates attract each other, and the force should not be dependent on how you've calculated it. So that's an example of calculation associated with energy, a little more complicated because of the need to take into consideration all forms of energy. But it's an important aspect of things. And you've seen that in 121, making sure that you account for all forms of energy. Now we have to be careful because the battery also can feed energy. Well, that concludes sort of what I wanted to share with you today. Hope that's going to be useful. Let me know if you have any questions.